Uh,
All right, so welcome back everybody to today's session of the Cardiff Analysis Seminar. I hope you all had an enjoyable Easter break. So we are back now for at least a couple of weeks before the early May bank holiday. And today we're delighted to have Peter Kuchment from Texas A&M, who very kindly joins us so early in the morning for him. And he will give a talk titled on dispersion relations of discrete periodic operators. So thank you very much, and over to you.
Thank you very much for introduction, Matteo. It's my pleasure to give a talk at Cardiff after a long time. Even on Zoom, it's still pleasure, and to see many people I know, and some people whose names I know. So I will be talking about dispersion relations of discrete periodic operators. So I will give some introduction to what it is, but I suspect that to many of you, I will be preaching to the choir, but it's better than the other way around. So first of all, what are periodic graphs? I will be talking if some of you expected me to talk about quantum graphs, I will not be talking about quantum graphs. These are just regular combinatorial discrete graphs, which in my view are somewhat harder and deeper than quantum. Quantum graphs have their advantages, but these guys, although they have been studied for eternity, still offer new things. So let us have an infinite graph, and we have the integer lattice group acting on it by transformations. The action is free, and we also assume co-compact action. Namely, this means, in discrete case, this means that there are only finitely many different orbits. In other words, there is finite set of vertices such that their shifts by this group cover the whole thing. And the fundamental domain is any such finite set of vertices that uniquely represent each orbit. For instance, this is a famous example. This is hexagonal lattice, or if you want to look at it this way, graphene. It's periodic with it has the group periodicity group Z2 with these two generating vectors. So if you shift along these vectors, everything repeats. And here is a shaded fundamental domain which has only two vertices and three edges. Everything else can be obtained by shifting. So this is the fundamental domain. It has, like physicists would say, just two atoms. So those periodic graphs will be my object to study. By the way, recently there have been many advances when you have a non-abelian periodicity group, but it's somewhat different animal, and I will not be talking about this. Okay, so now let us have an operator, a difference operator on graph. Let's call it L. What does it mean? It's essentially infinite matrix whose rows and columns are indexes by vertices. So functions that I will consider, they will be taking values at vertices, not along the edges, but at vertices. And difference operator is just matrix acting on those. So this infinite matrix whose rows and columns are indexed by vertices. We assume that this matrix is periodic with the same group action. So you don't see any difference if you shift. And we also assume that it has finite order. This will correspond to, in the case of differential operators of finite order, which means that each row of this matrix has only finitely many non-zero entries. Or geometrically, it means that each vertex, the value at each vertex, if you apply this matrix, will involve only a few neighbors, finitely many neighbors. Again, in PDEs, this corresponds to finite order, to the differential order of the operator. Example, the most famous example is Laplace operators. There are different versions of them, of such operators. You will see another one later, but this is the simplest. You take the value, you take a function on vertices, and when you apply this operator, its value at the vertex V, as I checked for misprints zillions of times, but there are still plenty of those. It's not V, it's A in this graph. So if you take function on vertices, you apply this operator to that function f, its value at the vertex A is the sum over all neighbors minus 3 times the value here. There are versions of this operator, y3, since this is the degree of the vertex. And I will not discuss other types of operators, since many results are very, very general. You can pick more or less any periodic discrete operators, difference operator of finite order, and they will work, but this is the simplest. So you take the value here minus, or the other way around, it depends whether your Laplacian is delta or minus delta. Here you take the sum over the neighbors minus triple the value here. Or maybe more understandable version, if you divide this by 3, you will take average over the neighbors minus the values here. For PD people, it reminds you the mean value formula for harmonic functions. So this is an example. Any questions so far? Interrupt me with questions. I like them. If none, then let's go forward. So now we introduce the notion of a character. So character of a group, of a abelian group, is multiplicative mapping from this group to numbers, to complex numbers, and such that the identity goes to 1. And all characters of the group Zn can be written in the following way. That's a standard exercise, that if G is a vector from this integer lattice, each character can be labeled by a vector k. In physics, they call it quasi-momentum, which is real or even complex. And this character looks like e to the power ik inner product with this G. If k is real, then this character is, as I say, unitary character. It has absolute value 1, and it lists all unitary representations of this group. But you can and should allow complex values of this k. Even in physics, they're important. And then this is non-unitary character, which corresponds to non-unitary representations. And for us, in discrete case, it's very, very frequently, it is more useful to consider, instead of those quasi-momenta k, their exponents. If you exponentiate each of the components of k's, you get a vector, a complex vector of, if k is real, it will be vector with components of absolute value 1. If k is complex, you can shift from this torus. This is so-called Flaquet multiplier. The reason for this is very simple. Since this function e to the power ik dot g is periodic with respect to k. Since if you shift k in such a way that k dot integer vector adds 2 pi, the value of the exponent doesn't change. So this go into Flaquet multipliers, it removes this non-uniqueness. It removes this non-uniqueness. So every character, if you look at it labeled as Z, with Z rather than K, that uniquely corresponds to the Z. So here is the way the character looks like in terms of again, misprint Z to the power J means Z1 to the power, this Z1 to the power J1 times Z2 to the power J2, etc. So these should be Z1, etc. Zn here. So these are integer powers of this vector Z, which G's could be negative. So if you take linear combinations of such things, you get what is in complex analysis is called Laurent polynomials. They are polynomials with respect to Z, but negative powers are allowed. Now we will be interested in functions on our graph that are automorphic with respect to this character. What it means, you don't need to know anything about homomorphic functions. This means that if you shift, you take function u at the vertex x and shift by a vector of periods g. So what should happen? You get the old value times this character. So when you shift by periods, the value of the function gets multiplied by a character. This is in the quasi-momentum representation. This is in Flaquet multiplier representation. Again, when you deal with PDEs, sometimes you prefer to work with those Ks in spite of them being not uniquely defined, and sometimes with these. In discrete case, you always prefer to deal with Flaquet multipliers. You will see why, since a complicated analytic problem will become algebraic. So such functions have many names. I call them automorphic functions, like coming from number theory. In PDEs, they are called Flaquet functions. In physics, they are called Bloch functions. But the meaning is the same, that if you shift, you only get multiplied by this. Another word is quasi-periodic function. So there are many names for this thing. And now let us look again at our Laplace operator. It doesn't have to be Laplace, but it's a good example. And I changed notations on you. Well, the same with the Zoom lectures. I spend the whole day polishing my slides, and then I find misprints on every single slide in spite of that. You know, they say that they took big care of preparing the encyclopedia. They corrected it 20 times, and still on the title page it said British Encyclopedia. So that's my case. So this is Laplace operator. What it does, it sums over all neighbors. This tilde means that W is connected by an edge with V minus triple or whatever the degree of the vertex value in the middle. Now, in PDEs, we all know that there is very important function that tells you a lot about operator. It's the symbol. When you replace ddx by some complex variable xi, instead of differential operator, you get a polynomial. The same happens here. There is a symbol, and you can understand how to introduce it again if you're coming from PDE. To get the symbol of differential operator, you need to apply it to exponentials. And you do the same here. Instead of exponentials, you take those automorphic functions with this property, and apply the operator to them. So now let me look again at this picture. So look what happens. So let's say I want to compute the value. You see what happens since the graph is periodic, only these two vertices are relevant. Everything else, we need to know what operator does on these two vertices, since it's periodic and everything else repeats. So let's look at this point A. To compute the value of Laplacian at the point A, what you need to do, you need to add the values at these neighboring points and subtract the value at A. But look, you only want to see the values at A and B, since all others shouldn't be relevant. How can you do this? If your function is automorphic, we know what happens with the shift. We exactly know what happens with the shift. And you can notice that first of all, A and B we have in hands, but the values here can be obtained by appropriate shifts of these from these two vertices. Therefore, for instance, if you go from B down, meaning shifting by minus vector E2, you are here. And you know on automorphic functions, what is the relation? If you know value here, you can find here. The same here. And if you go to the vertex B, the same happens. One neighbor is A, you have the value f of A, but these two neighbors you don't know. But look, they can be obtained by shifts from just these two vertices. Since these two vertices, if you shift them, cover the whole thing. In other words, if you know that your function is automorphic, you only need to know the values at the points A and B. For instance, this is what I wrote, that at the point B prime, which was one down from B, that's the value. So it's expressed in terms of the value at the point B. At the point B2 prime, you have this. And you can do this for all those neighbors. And then the action of your operator L on an automorphic function with a Floquet multiplier Z can be expressed as a two-dimensional matrix. The value LU at A, if you put all those calculations together, you have this. And at B, you have Z. In other words, L is multiplication by this matrix, 2 by 2 matrix, L of Z. And this L of Z is what is the symbol for differential operators, So now on automorphic functions with this given Z, our operator acts as this 2 by 2 matrix. And this 2 by 2 matrix is not exactly polynomial, but it's polynomial with respect to positive and negative integer powers of those Z's. Negative power, since it's not arbitrary polynomial, it's Laurent polynomial, it has only those negative powers, you can multiply by Z1, Z2, and everything will become algebraic. You will get only polynomials. And this is the crucial difference between PDEs, continuous case, and discrete case. In discrete case, the symbol L of Z, or in discrete case, you also usually call it L of K. You look at the dependence on quasi-momentum, is algebraic function of Z. It's not true for PDEs. And you will see that it makes significant difference. Now, what is the dispersion relation? That's the object that I declared I will be discussing. Dispersion relation, it comes in two incarnations, real or complex. Both are important. Dispersion relation is named from physics. Mathematicians frequently use the word Bloch variety. What it is the set of pairs K and lambda, or Z and lambda for us, it will be mostly Z on lambda, such that this equation, that eigenvalue problem LU equals lambda U, has a solution which is automorphic with this given K. So in other words, if you give K or equivalently Z, this equation is in two-dimensional space in my example. And that's one way to describe it. And more explicit way is, since we know that L is just a matrix that polynomially depends on Z, or not exactly polynomially, it's exponentially depends on K. So to detect whether there is a solution, you have to take determinant of this difference and write that it's equal to 0. And you get what is called dispersion relation. It is the set in the space of K's and lambdas, set of zeros of this equation. Again, in PDEs, you can do similar things, but those determinants will be infinite. And you have to deal with operator theory to regularize them, and they will not be algebraic functions of the Z, they will be analytic functions, and the whole thing gets hairier. However, the gist of it is the same. So this dispersion relation contains pairs K lambda, for which your equation, your eigenvalue problem for your Laplacian, has not just a solution, but solution which is automorphic with respect to K. In other words, automorphic solution can be written as follows. U of x must be periodic function times this exponential. Okay. Another way to look at it is the following. So if you fix K or Z, it's equivalent. I will be switching between them. Very soon I will move completely to Z's. If you fix K or Z, you have a finite dimensional eigenvalue problem. In my previous example, it's two-dimensional. So it has two eigenvalues. But if your fundamental domain has more atoms, more vertices, it will be higher dimension. So what you do, you fix K, and over this K, you point the eigenvalues along the lambda axis. The first eigenvalue is the second. In my previous examples, there will be no more. But if you have your fundamental domain has 3 vertices, there will be the third, fourth, etc. So you see, you fixed this K and you look for solutions. It's eigenvalue, finite dimensional eigenvalue problem. So for a fixed K, you plot those points. It's multiple valued function that for each K gives you the spectrum of this lambda L of K. And since we are in finite dimensional situation, this is, it has finitely many values, but it's multiple valued function. So this is, its graph is a dispersion relation. And those guys have names. If this is the first, if you follow the first eigenvalue, this is this lambda 1 of K, this the lower sheet, is called the first band function, the next, the second band function, etc. You cannot do this when K is not real, since the spectrum become complex, and you cannot already tell which eigenvalue is first, which is the second. Complex numbers you cannot order in increasing order, but at least in over real case, the spectrum is real. You can tell this is the smallest, the next, and the next eigenvalue. So these are the notions that I will need. Now, the well-known thing is that the range of this function is the spectrum of your original operator. So original operator didn't know anything about automorphic functions. It was operator in L2 on the whole infinite graph. And the thing is that in this picture, if you project this dispersion relation on lambda axis, you will have the spectrum of your original operator. And that's why it's a very useful tool in such problems, and that's why physicists love it. Since when you project, you get continuous spectrum, but for each K you have discrete spectrum. And this is a simplistic picture. If you imagine K one-dimensional, let's say these red are 3 branches of dispersion relation. You project them, and each branch gives you a closed segment on the lambda axis, which is called the band of the spectrum. Some of the parts of lambda axis might stay open. They are called gaps of the spectrum. And some bands might overlap. You see here on this picture, the band, the first band, if you project it, it overlaps with the projection of the second band, so they can overlap. So essentially, again, I'm preaching to the choir, but the result is this band gap structure of the spectrum. So the spectrum consists of closed finite intervals, of union closed finite intervals that may overlap, like here. They're called spectral bands. What is not covered is called spectral gap. Now, some propaganda here and additional information. Additional information is that one can deduce from this picture that the spectrum of operator L, when I say L, I mean without any automorphicity condition, and just in L2 on the whole graph. It consists as a spectrum of any self-adjoint operator, and like we learned in real analysis, any measure can be on the line can be split into three parts: absolutely continuous, pure point, and singularly continuous. The same with the spectrum. Spectrum is famously divided into absolutely continuous, pure point, and singular continuous part. The very general fact that doesn't use anything much except periodicity in graph case, and in PDE case, it's additionally you would want to have equation elliptic or hyperelliptic. It's very general, simple statement that there is no singular continuous spectrum here. Only absolutely continuous and pure point. So I remind you what is pure point. Pure point spectrum are the lambdas for which there are L2 eigenfunctions. You usually have an eigenfunction for any point of the spectrum, but those could be not truly eigenfunctions. They are not in L2, they will be growing. But pure point spectrum consists of lambdas for which there are true L2 eigenfunctions. One of the major questions is, and major expectations, that there is no pure point spectrum as well. It's interesting that geometrically, it has the following meaning. One can prove that, that if you have lambda here in the pure point spectrum, it's equivalent to the fact that you have a piece of this dispersion relation, which is just a plane, which is completely flat. And this is old observation by Larry Thomas, and it helps to prove very frequently absence of pure point spectrum, namely that if it has this flat part, it actually extends in the complex domain as well. So how can you try to prove that there is no flat part? Flat part means that no matter what K you pick, you have the same lambda. So what you do, the standard trick is you go to domain of complex non-physical lambdas, you go somewhere far away in complex domain, and over there you prove that this lambda is not in the spectrum. That's it. So you don't have this flat part. That's now, so this is absence of pure point spectrum is absence of flat branches. And for PDs, it's almost done, but not completely. What is the relevance of this spectral structure? For instance, some semiconductors, they are semiconductors due to the presence of spectral gaps. So spectral gaps, that's what makes semiconductor. And there are new types of, already not very new, almost 30 years old, types of material photonic crystals, they're optical analogs of semiconductors. And over there, the fight had been for a long time to find materials where there are spectral gaps. Now, the geometry of dispersion relation is important for many physics and mathematics issues. For instance, in solid-state physics, there is a notion of effective masses. I will not tell you right now. If I have time, I'll tell you later what it is. It is based upon some expected but still not proven property of dispersion relations. The amazing conductivity of this, especially famous in Britain material graphene, is based on geometry of dispersion relation. Namely, it essentially based graphene arises when you have this conical structure, when the two bands of dispersion relation touch conically. These are not true geometric cones, but infinitesimally they look like. That's what makes graphene. Even more hot topic nowadays is topological insulators. These are materials that in the bulk, in the interior, they don't conduct electricity, they're insulators, but on the surface, you never have infinite material, you always have a chunk. It has a surface, on the surface they're perfect conductors. And the reason of this is, as the name suggests, topological, and this topology again is hidden in dispersion relation. I will not tell you how. So leave it too much. It is also important for Anderson localization or metal insulator transition, for embedded spectral eigenvalues and many other things. Mathematically, it also implies what decay of Green's function you expect. It implies what kind of Liouville theorems you have, etc. I will not dwell on this. It's just propaganda that this object dispersion relation is important. Okay. Okay. Now there is another important surface, so-called Fermi surface. So how do I remove this? I annotated, I don't know how to remove it. Okay. If this is your Bloch variety or dispersion relation of your operator, and you fix lambda, then you take level curve or level surface of this level lambda, so you cross this graph with the plane, and this is the level set, the set on which this dispersion relation has the value lambda. This is so-called Fermi surface, and Fermi surface is labeled by this lambda. So this is just level surface of this multiple valued function. In physics, Fermi surface, the name Fermi surface is used only for one very specific value of energy lambda, but we are mathematicians, we can call anything we want to, any name. So we call the surface for any lambda Fermi surface of this level lambda. Now, what are the issues here? what are the problems here. And I will list problems and what is known, what is not known. As I mentioned, absolute continuity of the spectrum, it is equivalent to absence of flat components and absence of true eigenfunctions, L2 eigenfunctions. It's expected that all periodic elliptic coefficients with sufficiently nice coefficients, nice so that uniqueness of continuation theorems hold, which is most of the cases. But however, it's still not proven in full generality. There have been major advances. I'm sorry, I definitely would miss some names since this is old history. I haven't been following recent developments, so there might be more results. For higher order operators, in spite of some people believing it in old days, for higher order operators, this is not true. You can have L2 and even compactly supported eigenfunctions. So this is specificity of second order operator. So this is mostly solved. No? There is a stronger conjecture. The Bloch variety is irreducible. Let me explain what it means. Where is my Bloch variety? Bloch variety is a set of zeros of an analytic function. In this case, algebraic. You know, if you multiply two analytic functions that don't know about each other, multiply them and look at them as the set of zeros, it will consist of two unrelated set of zeros, so one factor and of another factor. These are components. So if you cannot split into such irreducible components, in other words, if you cannot represent this dispersion relation as a union of two independent analytic sets, it's called irreducible. Irreducibility, if it's irreducible, essentially it means the following, that if you know any tiny piece of the surface, it uniquely determines the whole thing. So if you know eigenvalues lambda for, let's say, lowest eigenvalue, lambda 1, for some open set of case, you know everything. That's what reducibility means. Reducibility would mean that there are hidden things that you don't see here. This is much stronger conjecture than absolute continuity. Why? Since if you don't have absolute continuity, you have this flat part, as I discussed. But this flat part is separate component that the rest doesn't know about. So you have reducibility. So irreducibility is much stronger conjecture than absolute continuity. It has been proven only in 2D for Schrödinger operators with really advanced techniques. No other cases known. Irreducibility of Fermi surface. Fermi surface is just one layer. It's also analytic set. Set zero is analytic set. It's also known only in that case. It's also important for spectral theory. What I will be mostly interested in is the structure of gap edges. Let us see. So you remember the projection of Bloch variety of dispersion relation on lambda axis gives you the spectrum. So when the spectral gap begins, this means that you had maximum here, or maybe minimum. So the maximum corresponds to edge of spectral gap. And there is a conjecture. Everyone in physics and in mathematics knows that it is true. No one has been able to prove it. That how does this maximum look like? In principle, the maximum can be flat. It can be very flat. Or it can be non-isolated. You can have like Mexican head of this maxima, like crater, edge of crater. Conjecture is that generically, what I mean generically? For instance, if you're talking about Schrodinger operator, you perturb potential. And with probability 1, you see non-degenerate extreme. Non-degenerate meaning that it's parabolic. The Hessian is non-degenerate. It's truly parabolic. It's not flat. It implies a lot of stuff in physics and mathematics. Everyone knows that it should be true. No one has been able to prove it. So this has been, there was very little progress in this direction. Partial progress by Klopp and Ralston, and a little bit more significant, but only very limited case by Calandre-Verdier.
Sorry, can I ask a question? So two questions actually. So the if and only if condition relating the absence of pure point spectrum and no flat components, are both directions clear? I mean, it's clear that if you don't have point spectrum, you don't have flat bits, but is the other way around, is that a simple thing, or is that?
Actually, this is the harder direction. The other direction is easy, since to prove that if you have L2 eigenfunction, you can deduce quickly that this Fermi surface, which is a section, has positive measure. But set of zero analytic function can have positive measure only if it's a whole space. The other, but it's not very hard. It's done. For instance, you can look into force volume or Eden-Simon, or in my survey in Bulletin 4 years ago or something. So this is not hard.
And another question. So the gap edges can be only obtained by extrema, as you mentioned, and not, you can't have a situation with some kind of asymptote at infinity or something?
No. The thing is, that's a very good question. No one has ever asked me. That's a very good question, and the answer is no. There is no infinity. If you recall, K, this quasi-momentum K, is defined only up to some period. You remember, e to the power ik, if you add 2 pi, nothing changes. This means that K is actually not on plane, it's on a torus. So there is no infinity. And that's why, by the way, those spectral bands are finite segments. Since you have lambda of K defined on compact on torus. So its range is finite. Anything else? Okay. And there was also old belief among many, but not all physicists, that if you look, so how to find the spectrum, you need to find then the ends of the gaps, those extrema. And the belief by many physicists used to be that you'd only need to look at, not at all case, searching for those extrema, but only for those that are in some sense symmetric. Usually in your crystal, besides shifts periodicity, you have some point symmetry, rotation, reflections, etc. And so they were looking only among those symmetric points, and it's incorrect. Okay. Now, what is known in discrete case? In discrete case, irreducibility is not true in general, since you can have pure point spectrum. And that's actually more interesting. If you have a pure point spectrum, you have L2 eigenfunction. In fact, you have compactly supported eigenfunctions, and they generate the whole subspace. I did this in a billion case, and Veselic then proved for amenable group action. So the existence of L2 eigenfunction is the same as the existence of compactly supported ones. That's strange. I will not talk about irreducibility anymore. I will be interested in non-degeneracy of the extreme. So naturally, it's such a hard question in PDE. So you look at the discrete case. What Ops, Filonov, and Kachkovsky constructed simple examples of two atomic structures on the plane, just two vertices, like in one of my examples, different graph, but still two vertices periodically shifted. I actually wrote the operator here, and Laplace type operator such that no matter how you perturb, so what are the freedoms? This potential, since you have only two atoms, but there are two values of potential, one at one atom, another at another atom. And that's your degree of freedom. And they constructed an example when they show that no matter how you perturb this potential, you still have degenerate extrema. Well, since I still believe in PDE conjectures that generically, when you perturb potential, things like that, there should be non-degeneracy. And here is counterexample. What could be the reason? If you have ever dealt with things like singularity theory or transversality theorem, Sartre theorem, the generic statements that something happens generically, let's say with probability 1, usually you need for that sufficiently big freedom of changing parameters. Here you have only two. So what I thought about, let's take a graph where you have more parameters. So again, these are two atoms, and they shifted periodically, just two atoms. But now I allow all edges connections to neighboring squares. So all those edges are allowed. The edges that are drawn in dotted lines, they are not needed since they are by shift obtained from those. So if you take the edges with bold lines and shift them periodically, you get all of those. So there are 9 independent possible edges here. Now, how do we attach parameters to them? Since potential is defined at vertices, it will have just two values. Instead of potentials, I will consider this kind of Laplace-Beltrami operator. I give each edge a weight, and there will be 9 weights. And for these are the weights. Edge E is assigned a non-negative weight alpha V. And this is our operator. This is analog of Laplace-Beltrami operator on the Riemannian manifold. So this is like gradient. This analog of divergence type operator. Divergence, factor, gradient. This difference is gradient. This is this factor like diffusion coefficient. And the sum is divergence. So this is type of Laplace operator. And now the question is, if I have complete freedom of changing those weights, is it true that generically I can make all band edges non-degenerate? And first, so you look at the values of alpha. Alpha is in 9-dimensional space now. And I want to look at alphas for which the dispersion relation doesn't have any degenerate critical points, not just maximum, minimum, but all critical points. And simple algebraic geometry statement is that there is dichotomy. There are two options. Either for almost all alphas, the edges are non-degenerate, or for almost all alpha, there is a degenerate edge. For almost means the following. If you look at the set of alpha for which there exists non-degenerate critical point, that either all those alphas are in small algebraic subset, set of zeros algebraic function, or it contains a complement of such set. So it's almost always or almost never. So to prove that you have almost always non-degeneracy, thus it's sufficient to do the following. If I can find a point alpha in this parameter space, such that I can prove that in the neighborhood of this alpha, there are no degenerate points, I am done. Since according to dichotomy, you see, if alpha is restricted to algebraic subset, it cannot have open parts. So if I found a small open set where everything is good, then it is the whole space of alphas except maybe thin algebraic subset. That's it. It's not hard to find a point where things are good, hard to conclude that in the neighborhood they are also good. This is algebraic geometry. So for these operators that I introduced, our theorem is that the result is good. So for all alphas, all weights, except a thin algebraic subset, there are no degenerate critical points. So in spite of Filonov-Krachkovsky example, where they have too little freedom, only 2-dimensional freedom, we have 9-dimensional freedom, and so I'm running out of time, but I will be able to sketch. We have 3 proofs. Some of them proofs in quotation marks. The first proof is the following. Look, we have 12-dimensional space of parameters. Z, which is 2-dimensional, local multiplier, lambda is 1-dimensional, and alpha is 9-dimensional. So our dispersion relation sits in this 12-dimensional space. And now I project onto 9-dimensional space of alphas. Now look, the condition of being critical point and degenerate critical point has 4 algebraic conditions. First is that you first of all have to be on the block variety. You should satisfy this determinant equal to 0. Second, it should be critical point. 2 derivatives should be 0 in 2 directions of z. That's 2 more equations. And being degenerate in 1 more condition, that matrix of Hessian is degenerate. So you have 4 conditions in 12-dimensional space. So you expect that the set is 8-dimensional. You took away 4 dimensions, and you project onto 9-dimensional space. It should be okay. 8-dimensional surface cannot cover much of a 9-dimensional space when you project. The problem is that count of those equations is insufficient. Imagine that some of those are related. Then you have less conditions than you expect. And then you might end up with 9-dimensional space, for instance, that can easily cover the whole 9-dimensional space of lambdas, of alphas. And the first proof was with computational algebraic geometry. What we did, we found all irreducible components of this set of interest. And we computed all their dimensions. And none of them was more than 8-dimensional. That's it. However, it's not completely legal proof, since those algebraic geometry computations are not certifiable. So they are not certified as a rigorous proofs. There could be that you miss something. The second, even a bigger quotation marks proof was, okay, we know that there is dichotomy. Either almost everything is good or almost everything is bad. So if you pick random alpha and check, then with probability 1, you get correct answer. You take random alpha, look, if there are no critical points that are degenerate, then it's probability 1 that they are almost never there. But then the question arises, what does it mean, random? How many of them you should check? We did this and it works, but it's not rigorous. But for practical purposes, it's pretty good. You know, there is this dichotomy, which holds not only for this operator, but for anything in the world. You try randomly, you use random number generators, try random parameters. If for a few of them, even for one of them, it's good, you're pretty safe. That statement is
do you have a canonical way to put a probability measure on the alphas?
Yes, there are ways to do this. Even there are arguments in which you can only try integers, but again, still it's not a mathematical. And the third was rigorous proof, and I just finished telling you how it works. It works as follows. So let me annotate. Oh, did I stop share?
Yes, you did.
Why did I do this? No. What I want to annotate. So here is the idea. Why now it doesn't annotate? No, it doesn't work. So the idea is that what can go wrong? I told you that it's easy to find a good point alpha. But if you look at the set of your interest is somewhere up there, it's a dispersion relation. You project it, you know it covered good one alpha. But how can you prove that it covers the whole neighborhood, that the neighborhood of alphas is also good? Since what can happen, it can go like this, tangentially. So on one side of alphas is covered, another is not covered, or maybe it's just vertical. Maybe your algebraic set is just vertical, it projects into one point. The thing is that if it's vertical, there are many points over alpha CG. Algebraic geometry, and some, so the bad thing is that there are points on your dispersion curve that when you project, they move tangentially, not transversally to that. Mm-hmm. If projection is transversal to your surface, it covers open set. So and it's a difficult algebraic geometry. For this specific case, one can prove with some algebraic geometry techniques, very advanced techniques, that over each point cannot be more than 32 points hanging. And then you find all 32 points. If things were going bad, some of them would collapse to 1. You would have multiplicity. But you compute them and you see that you have exactly 32. And therefore, by algebraic geometry argument, you prove that this set where there are no critical points covers open subset under projection. And so this is the result. Another thing is, I said that the ballpark idea is that the more parameters you have, the better chances for non-degeneracy. For instance, I had only metric here. If I add potentials, can things get worse? The ballpark idea is they shouldn't be. And there is this conjecture that if you have some parameter space alpha, let's say potentials, and you have this genericity, and now you allow freedom of changing diffusion coefficient additionally. They shouldn't spoil the thing. We don't know how to prove it in a discrete case, but for this particular graph, we can prove it. That if you found the situation of alphas where everything is good, if you add more, they cannot become bad. And that's what I want to say. It was published last year in Journal of Mathematical Physics.
Thank you very much for the talks. I'll clap physically and people will clap virtually somewhere or somewhere. So thank you very much for the nice talk. So we had a few questions already. Do we have more questions for the speaker?
Can I ask,
Please go ahead.
what additional assumptions are needed to make the Bethe-Sommerfeld conjecture hold for these periodic graphs?
Well, I don't know. Periodic graphs don't like Bethe-Sommerfeld. You know this, that you can easily, Bethe-Sommerfeld conjecture says that you have finitely many gaps only. On any graph, not only periodic, you can open infinitely many gaps. So I don't know.
Yeah, I guess I was just wondering if some, I mean, for differential equations, of course, one dimension is special. It's false in one dimension, and then higher dimensions, it's true. Actually, I think in higher dimensions has to be correctly interpreted. I mean, for a waveguide, for example, I think it's, from what I remember, Bethe-Sommerfeld is false. I think that was proved by Borisov last year.
Yes, but this is what expected, since that's the same thing as with graphs.
Right.
You see, for waveguides, there are. It's related to things like irreducibility. If you have reducibility of block varieties, it essentially means that there are two operators there. One you see and another is hidden.
Mm-hmm.
And so there are two spectra that knows nothing about each other. And for instance, you can easily get embedded eigenvalues.
Mm-hmm.
But this is fake, since eigenvalue comes from one part of operator, one mode, and so embedded into spectrum of another. So I wouldn't be surprised. I don't know. I don't know whether anyone looked at this, whether I don't know the answer about Bethe-Sommerfeld.
Thank you. Thanks.
More questions for the speaker.
I was wondering what is special about 2 dimensions.
There is nothing special about 2 dimensions.
You said that the flat band thing is proven only in 2 dimensions, that there are no flat bands.
No. No flat bands is proven in very wide variety of cases. It's not about 2 dimensions. It was about order over the operator. Second order operators or higher. And the difference is very significant. In second order operators, they have uniqueness of continuation, which actually graphs don't have. And that's what makes them different. That's why you can have compactly supported eigenfunctions. Second order elliptic operators have uniqueness of continuation. Solution that vanishes on any small part or even has 1, 0 in infinite order is identically 0. Higher order operators don't have this property. They can easily, there are examples of fourth order operators that have compactly supported eigenfunctions. So this is about uniqueness of continuation. And one difference with graphs is that they don't have uniqueness of continuation, which is sometimes a blessing, and sometimes it's a very bad thing to have.
Okay.
So it's not about dimension. Actually here, graphs were not planar. The graphs I showed, they were not planar. It doesn't matter.
I think, sorry, I think I meant to ask what you said about the irreducibility of the block.
Oh, irreducibility. Well, it's hard to say what is special. It's such an awfully hard question. It involves, you see, how those things are proven in discrete case. You have algebraicity. All your sets in terms of multipliers are algebraic sets. In algebraic geometry, there is this standard trick: you compactify. You go to infinity, to projective spaces. And very frequently when you go far away, things get clearer. Unfortunately, in analytic case, there is no such thing. So Knorer and Trubowitz had to invent some very intricate directional compactifications in analytic case that they could handle. And it's even hard to tell what is special. It's surprising that it works in 2D, since it's mind-boggling construction. So, but it is expected that it's true. It would have been nice. This essentially it gives you rigidity. That, as I said, if for some fixed quasi-momentum and one lambda, you know everything that happens near this lambda for that quasi-momentum, it determines completely the whole picture. You know, there is a whole book by Giesecker, Trubowitz, Knorer and Trubowitz about spectral theory, Fermi surfaces of discrete periodic operators on Z2. And the whole book, and it involves everything up to Deline's work. So it is something really complicated even in discrete case.
I see.
Some progress recently was done, not only in Z2, but in Zn, in this discrete situation. In their book, they only proved, for instance, the Fermi surface in dimension 2 is irreducible except finitely many lambdas. And Vincile Liu from our department recently proved in any dimensions that it is true for all but one value of lambda, and one that he pinpointed, which is this. And so it is difficult stuff. It's simpler than in continuous case, but it's still mind-boggling.
Thank you.
Do we have any more questions? If not, then let's thank the speaker again for the very nice talk.
Thank you very much.
Thank you very much.
Hi, Christine.